welcome back to the track. And this talk will be presented by two speakers. And this talk is targeted at the beginner to explore the architecture of the open source tool stack for the making robot project. For the, from the software begin to building tool, the simulation software to the test your robot. So speaker will help you to discover these tools. Let's welcome the two speakers, Vincent and Arthur.
So, hello everyone, I'm Vincent and this is Arthur. Thank you for coming today. This is our first time talking for COSCUP, so thank you. And we're going to talk about our open source stack for how we made our robots. Little disclaimer, it's for really beginners, so we are not going to go really deep into each tool. So just so you know, thank you.
All right, so basically this whole talk idea or this whole project started because we wanted to make a robot for a competition that is called the Micromouse competition. So the Micromouse competition is an international competition. So it happens in Taiwan, also happens in the US, in the UK, even in Japan. And as you can see on this image here, the goal of the competition is to build a very small robot. Maybe we can show it here. And this robot must solve a maze, so go from the edge of the maze, like the entrance, to the middle of the maze. So that's the whole point, and the idea is you have to be as fast as possible, so the fastest robot wins. So, of course, this is quite, it looks simple at first glance, but it's actually quite complex. And if you do some robotics, you will know that there are a lot of different moving parts you need to take care of. So if you want to make a robot, for example, you need to have your robot move, of course, but it also needs to know where it is. It also needs to see, right? In that case, we need to see the walls of the maze. So it means you need to have sensors, maybe a camera, maybe laser sensors. You need to have motors to move the robot. And you need to combine everything. So you need to maybe do your own electronics, or you need to also write your software to combine all of these complex components together. So that's a lot of work, basically. So now what we are going to talk about today is what did we pick to make our robot this year? And so, of course, to do such a project, you need a lot of things. So you need to have something to code, to manage this code, to collaborate together, to manage all the files we are going to produce during this project. And you also need a lot of tools to create and build a project. So that can mean anything from programming language to maybe even a 3D printer, design tools, everything like that. So that's quite a lot of things. And so everything we used here is open source. So I think that's pretty cool that you can make an entire robot with only open source tools. And today we are gonna have maybe a little tour of all of these tools together. Just a bit of a disclaimer. You don't have to do everything by yourself, right? Here we talk about PCB design, we talk about, so PCB is the electronics basically, we talk about coding, etc. But in some cases there are some simpler things you can use. So for example, we will talk about Rust on the programming side. You can just use an Arduino and C and write very simple code, right? But yeah, we want to show you maybe everything that you can do in details. So we talk about, as I said, software, mechanics, and electronics, and we are going to start with the software, with Vincent.
Okay, thank you. So first of all, when you create software, you need to often collaborate if you're working with other people, and for this you need some infrastructure to collaborate. We also needed some version management, so I'm pretty sure you heard about Git. If you didn't, Git is a tool to help you keep the version of your code and reverse if you did some mistakes, and merge code together. We also need a tool who will be compatible with CI. If you don't know CI, basically it's the set of tools that will automate building and testing your code, so you can make sure that when you make changes to your code, it won't break. So you could have used GitHub, which is like hosted by a company for you. Use GitLab as well, but we wanted something self-hosted and where we own the data and we have control over the platform. So we self-hosted Gitee. You can also use ForgeJo, which is like another fork of it. And it has Git VCS, so version control software, as I said. And what I really like also about it is that you also have like issue management and PR management. What are those? Is basically when you have a feature you want to add to your project, you can define it and you can keep track of it. So it's very nice for collaboration. It also has a CI runner, so it means that you can, on your own hardware, run the test and build your code automatically when you're collaborating. And we self-hosted it on a Proxmox machine, but you can do this on any like little like Raspberry Pi and anything. If you don't want to host it, there is like some platform like Codeberg who also hosts ForgeJo. That is what it looks like. I think you're pretty familiar with this if you ever use GitHub. So the interface of Gitee is very familiar, like GitHub. They try to reproduce a quite similar interface, and it's quite easy to use. And it's actually a way faster interface than GitHub. Second, as I said, we need to build and test our code automatically. Because, for example, you want to add to your robot a feature to be able to see walls. But you want to make sure that you won't break, for example, the motor code who makes it run. And to make sure that you don't break the other parts of the robot, you can have automated platform called CI who will help you to do those things, to automatically check and test your code. So for this, Gitee has its own runner called the Gitee Actions. Of course, there is a lot of other things like I think Drone CI, Woodpecker, and things like this. But we chose to use the one which is like compatible by default with Gitee, and it has very nice integrated workflow, and it also supports the very similar syntax to GitHub Actions. So if you use GitHub Actions, you can actually use Gitee Actions as well. And it looks like this. So you can see all the different steps of checks and tests that you have and build, and you can make sure that for every code change you made, everything is still working properly. Then, I don't know if it ever happened to you, but you have your friend, he made a code, and he tells you, it runs on my machine. And then you come, you take the same code, you put it on your machine, and it doesn't work. And maybe it worked on the automated check, but it doesn't on yours, or maybe it works on yours, but it doesn't work on the automated checks, and it's very annoying. So some people will use maybe Docker or some containers to fix this issue, but we choose to use another kind of tool. It's called declarative dependency management. So for this kind of things, there is two main players in this area. There is like Nix and GoX. If you like Lisp, you can use GoX. If not, I recommend using Nix. And it's very nice to describe in a file all your dependencies and fix their versions, so that you make sure on two different computers you have the same versions of libraries, so that it won't break between the builds. It's also very nice, as I said, for CI, so that the automated tests have the same results both on your platform and on your local development machine. So this is a little example of code for Nix. And you can see here at the beginning, we will specify the versions of the packages and libraries and dependencies we have. And then at the make sure part here, you can define what are the dependencies you have. So this snippet here is actually what I used to make this presentation. We use the tool called Presenterm and Ghosty. So we can just like define the dependency here and make sure that on both our computers we have those. And then we need to choose a programming language. So for embedded system, usually you will choose C because it was the most used one. But if you want a more modern language with, and you don't want to care about memory safety, because sometimes you can spend a lot of time debugging memory safety issues, then Rust is quite a good alternative, actually. It has a very nice embedded system support and community. They made a lot of tools that can support STM32, etc. So it's quite a rich environment, and for me, way nicer to use actually than the C environment for embedded system. So you can give it a try. Although I have to tell you that Rust language has a way steeper slope of learning slope than other languages, because it has like different concepts for memory management. So you need to know about this. And then you need an embedded framework. So you might have heard of ROS. If you are interested in ROS, I invite you to listen to the talk afterwards, where they will be talking about ROS more in detail. But for us, we wanted to use something else. We needed the real-time capabilities. So you might have heard of something called FreeRTOS. It's the one which is the most used in C for embedded development. But in the Rust ecosystem, there is alternatives that are also very convenient and also support the kind of hardware we had. So we had the STM32 chip, so basically it's the brain of the little robot, and we needed to have support for it with our programming language. Rust has it. So the framework we used is called Embassy. There is another one in the Rust ecosystem called RTIC, but there is more boilerplate code, and Embassy has a very nice set of tools, so we choose this one. It has great support for STM32 MCUs, as well as other families of MCUs, and a very nice type-safe way to use it. I will show you later a snippet of the code. It also lets you easily test your code thanks to time mock driver. It means like you can manually increase time in your simulation while reusing the same code you had. And it's using async. This is like a specifics of Rust. If you don't know Rust specifically, it's fine. But for the one who use Rust, it's using asynchronous calls. So this is a little snippet of Embassy. As you can see here, I removed some imports to simplify the snippets here. But in the main loop here, we initialize our peripherals at the line where there is let p equal here. And on the second line, we here specify which pin of the MCU we want to use to make an output GPIO. And afterwards, in the loop here, we will easily toggle the pin high and low. So for example, you can blink a LED like this. And for the time management, you just use timer, and after how many time you want, like here in milliseconds, 500. So you can easily make a program that could cost more lines in C for the same purpose. So for me, it's quite convenient to use. I'm not sure whether you will have the same mileage, but I recommend using Embassy for your embedded code if you use Rust. And then we will talk about simulation with Arthur.
Yeah, thank you, Vincent. So as I said in the beginning of the talk, robotics is quite complex. Like you have many different moving parts. You have electronics, you have mechanics. And so when you want to test your robot, to either during development or after, it can be very slow, because if you just use your physical robot, you might have to deal with battery issue. You will have to deal with a lot of issues. And also you need to upload your code every time to the robot. So all of that, you need to construct a physical environment to test it. So all of that means that testing physically is costly. It's very important depending on what you are doing, but it can also be very costly. So something you can do to counteract this is make a simulation, right? Simulate your robot directly on your computer and see if your robot is doing what it should be doing, right? So for that, we use something called Webots. So Webots can simulate many things. You can simulate the physics of your robot. You can simulate what we call the actuators, so meaning the thing that act on the physical world. For example, the motors. You could have even some original things like a speaker. You can also simulate the sensors. So in our case, we have some laser sensors, but you could simulate something like a camera or something even more complex like LiDAR. The good thing with Webot is you can write the code of your robot in many different languages. You can use C, you can use C++, you can use Python, you can even use Java. You can use Rust. It's not officially supported, but you can use it. There is a few bindings. So the library we use here is called Webots RS, but there is another one called Forester Webots. I mean, there are a few ones, but basically it's not official, but you can use it. Webots is not the only player in that area, so you can see there is also Gazebo, which is pretty popular. I think both Gazebo and Webots work if you use Rust as well. There is also Copper on the Rust side, so this is a very pure Rust framework you can use for simulation. And Mujoko, I think, is more targeted toward if you need very precise like physics in your model. So this is how it looks actually on the right. Maybe it's a bit small, but you can see this is the viewport of Webots. You can see this is the maze. We actually made the maze virtually. And the nice thing is here we can swap different mazes. So you can see already the interest of having a simulation. And so you can see our little robot in blue on the left, and you have a few things. So you can construct your robot in Webots, and you can add the sensors and add the motors and everything. And the very nice thing about Webots is that the code that is running in the simulation is the same code that will run in the robot. And that's very important because you want to be testing your actual code. The only thing is you need to write some abstraction layer. The idea is, in reality, talking to your robot, talking to the motors, talking to the sensors will not be done in the same way in the simulation, right? Because in the simulation, they don't exist physically. It's just some piece of code you can call to get some data from the simulation, for example. So in both cases, you don't interact with your robot the same. So what you can do if you want to do that cleanly, you write what we call the HAR, which is hardware abstraction layer. Basically, it's just a small API to communicate either with a real robot or the simulation robot. And if you do that, you can just reuse the same code, both on the simulation and the robot, which is what you want to do most of the time. All right, and now that we talked about software, we're going to talk a bit about electronics.
Thank you, Arthur. So, for electronics, at first you will start with breadboards, with jump wires, as you can see on the right side here. So it's a lot of mess with all the wires everywhere. And you might spend a lot of time debugging issues like you didn't plug the wire correctly or the wire died, and lose a lot of time on this. And it's very painful. So there is a moment where you'll be like, I want something more reliable. And you want also something that has a smaller form factor. Because as we saw, the maze cells are quite small. And the bigger the robot, the harder it is to go into the maze. So how do we do this? Actually, you can use some tools to design your own PCB, printed circuit board. And with this, you will have way smaller form factor and way more reliable connections. No more jump wire that dies and doesn't work anymore. Of course, you might still break some capacitors, but that's something else. So, what can you use to design your own PCB? You can use KiCad. I don't know if I say properly, but yeah. So KiCad is an open source tool that lets you design your own PCB. There is a lot of resources online you can use to learn about this tool, especially on YouTube. And what can you do with it? So first you can do schematics capture. What is this? Basically, you will have this page here where you can place all the different components that you want to use for your robot. For example, I talked about the MCU earlier, the brain of the robot. You can see it's a big yellow rectangle on the left here, and all the connections it has. So it's more like of an abstract way of connection. It's not the actual connections that are on the hardware, the way it will take, but you say this component will be connected with this component, and you will place all your components like that. So you will map like this, all the different things you want to have on your robot and actually your printed circuit board. And later, you will do layout and routing. So layout and routing is that you will actually draw the routes that go from one component to another, both for the communication channels as well as the power channels. As you can see, it can get quite complicated after you finished, but the principles are actually quite simple. Don't be afraid of it. You just need to start, and it will come with time. And also, it lets you visualize in 3D what you made. So it's very nice to see, for example, if my button is properly placed on the board, or my headers are properly placed, etc. You can solve a lot of issues with that. So it's very convenient. And we have a little example here. That's the latest version of the board. Of course, you won't make it good the first time. You will have issues. For example, I misplaced the power connector and changed the polarity. I had to resolve them myself. So yeah, you will have trials and error, but that's normal. That's side projects. That's how it works. So you always need to redo, but that's fine. Chayo. And then you need to do manufacturing. So yeah, I'm not able to make a printed circuit board in my house. I cannot do that. I don't have the tools for that, but that's okay. There is great platforms like JLC PCB who can help you do that for you. There is other ones in Europe, but in Asia, I think the easiest is JLC PCB. They have a very nice website you can like send your manufacturing files to, and they will send you back the PCB well made after maybe like 2 weeks. It's actually quite quick. KiCad has some add-ons you can download that will help you to automatically do everything for you. They will export all the necessary files. You just need to give to that website, manufacturer website, and it just works. So that's very convenient. And once you have your PCB and you have your motors and you look at it and you're like, how do I put those together? Like, I cannot just put the motors on the PCB, maybe I can, but I need some structure. I have a battery, where do I put the battery? So you need to do some kind of mechanical design. So what tool can you use? You can use FreeCAD. Again, I'm not sure if I'm saying it properly, but yeah. FreeCAD, open source, and you can do 3D design for the parts you have. We use 3D printing. If you know other people who can help you do like laser cutting or other things, you can do that too. But for 3D printing, it's actually quite convenient. So you will first start with some 2D drawings, 2D design of, it's called parametric design. So you need to basically explain this length needs to be 20 centimeters, this length needs to be 3 millimeters, they need to be perpendicular. So you set all the properties of your 2D schematics. And afterward, you will add 3D properties. So for example, extrude, like make a cube from, like you have a square and you want to make a cube. So you extrude like this. It's called pad. And you can also make holes in your shapes. And after you have all those 3D features, you can export it to a format like 3MF. I think it's the format for the 3D printer slicers. And you can easily print it. So after you've done this, you can do things like this. So this is using PLA, I think, material for this version here. And then we have other version here are using carbon fiber, PETG, for the mechanical design here. And the printer here is Prosa. They have some open source tools that work with the Prosa printer. So there is also other open source tools can help you for all the 3D printing. And that's what we built. So the thing you see on the screen is actually the previous version of this one, because we had to put the sensors lower because the maze walls are very short, 5 centimeters. So yeah, I really encourage you to do your own project. Don't be afraid, start it. To be honest, I never did my own PCB before this project. So I had to like relearn everything. I learned a little bit in university, but I forgot everything. And I relearned everything, and I try, and it works now. So don't be afraid. Just try it out. I know sometimes we can be afraid. Oh, I might not do it well enough, or I don't know how to do this. Just try, trial, error, trial, error. There is a lot of resources online that are great to learn. So really, try and have fun. Thank you very much, and thank you, Arthur. You want to add something?
No, just wanted to say I think we have some time for Q&A. Yeah, like 5 minutes. So.
Okay. We have a 5 minutes Q&A session. So if you have a question, just come to the stage. I will deliver my microphone to you. Any question to our speaker?
Don't be afraid.
Yeah, don't be afraid.
I don't bite.
You can speak Mandarin too. So if you want to, you can speak Mandarin. Come to a stage. It's hard for me to run. Give me a round of applause, okay?
Yeah, I just have a quick question. It's about the versioning you do when you do all the testing to have like the same library on both of your computer. You didn't choose Docker for just because it's like optimized code, or just because on the robot you couldn't do Dockerization? Or why you choose like WeFix, like the?
You mean Nix? Why we choose Nix for the dependencies management?
Yeah.
Oh, first of all, it's a personal preference, and also like Docker, you need to have a daemon who also like work on your device. And if you don't want to have an extra like daemon working on your device and don't want to have all these containers, then actually Nix is quite simpler to use. I just do Nix shell and it runs, and it's quite convenient. And I think in Docker there is also some issue. Sometimes it's not the exact same like version of the dependency. You wanted to add something?
Yeah, I wonder about the devices also. If you use Docker, like maybe the access to the devices is a bit more like involved. But I guess, yeah, Nix is, even though I don't really use Nix by myself, but I recognize that it's a simpler solution for this kind of stuff.
Okay, cool.
Thank you so much.
And if you want to learn more about it, you can talk to me after, no problem.
He will wait you outside, and he won't leave. Any question for our speaker? Okay, I will jump. Okay. Thank you so much.
So first, appreciate the nice talk. And I'm the next speaker. So I personally, I also use Nix a lot and widely use it in my CI. But I do also need to run Docker because I'm also maintaining the middleware in Rust 2, which requires dedicated Rust 2 setups, like depends on Ubuntu. So that's why I need to use Docker a lot as well. So just a follow-up to the questions. And my current limitation of using Nix is it's hard to run on Mac OS and Windows. So do you guys have any better solutions on this?
We are mainly running Linux. We are Linux guys. We don't use Windows and Mac OS, so we... Sorry. I use NixOS and he uses Fedora for our development machines. Okay. And yeah, we stopped using Windows like 10 years ago, so...
Me too, actually, me too.
Okay.
So that's why I'm thinking that maybe we can propose a common database so that we can let at least the Mac OS could easily use to source the Nix environment. Right.
Yeah, I think Nix has some support for Mac OS, right?
But not all the package, like Rust. Like the Rust or any robotics frameworks.
Yeah, I think for Rust it's like a flake. They developed a third-party flake for Rust.
But only for Linux.
Yeah, okay, yeah.
So I think this is something good to work on an open source topic.
Yeah, that would be very nice actually, yes. I agree. Not all the Nix packages are available both on Linux and Mac OS, only a subset of it. Yeah. Thank you very much.
Thank you. One more question. Just one. Any question want to ask?
Any question?
Yes.
You can even ask what I eat for lunch.
Oh, Instagram. Any question about this topic?
The answer is nothing. I didn't eat.
Thank you so much.
Okay, here. Thank you. And I'm curious about how do you debug? Because it's a difficult. I don't know how to say it. It combines software and hardware when you face some problem, something maybe the robot didn't work as you supposed. Yeah.
Yes, thank you for the question. Indeed, this is a difficult thing in robotic, I think, in general, debugging. So that's why we invested a lot in simulation this time around. And I think it really paid off because in terms of development, debugging of what we code, it's really faster. We also use a telemetry system. I don't know if you know teleplot. It's a very simple telemetry system. Basically, it lets us plot all the variables in the robot, the speed, the position, etc. So we can kind of know what's happening in the robot. Now for the hardware testing, unfortunately, I think it's difficult. At some point, you have to put your robot down and do the task, and it will fail. And that's hours of difficulties, I guess.
And so he talked about teleplots. If you want to see what it is after, we can show you outside. But I want to add something is that to be able to have the same kind of telemetry both in the simulation and the real world, what we did is that even though external communication is forbidden during the competition, I added a header on top of this, and you can see there is an additional CPU, it's ESP32, and it can do Wi-Fi. So what I do with this is I flash on it a version of ESP hosted. ESP hosted is an open source firmware for the ESP32, and it will act as a Wi-Fi slave. So I can use my STM32 chip to communicate with this Wi-Fi slave, and we use the same telemetry prompt we use for our simulation to have the same graphs and same information about, for example, the position of the wheels, the speed of the robots, and all the internal state information. So that's how we do to actually debug the robot, both the same in the simulation and on the robot. We use Wi-Fi telemetry, so that we can have in real time on the laptop, we can see like what the robot thinks it's doing and all the different peripheral status. So that's what we use for debugging. I hope it answers your question. Thank you very much.
Thank you so much. Thank you much for the question, and thank you very much to our speaker, Vincent and Arthur. Give you a round of applause again. And next session will be start at 2:10. So welcome back. If you have any question about our speaker, you can go outside to the outside of the conference room. Okay.